Hello, so I'm glad to be here. My name is Erwan Pannier, and I'm going to talk to you about Radis, which is a fast line-by-line code for molecular spectroscopy. It's an open source project that's been developed over the past few years by about 20 contributors, of whom the main names are written here. We're quite happy that the code starts to be now used by a few groups. It has some very unique capabilities. And so the intention in being here is to present what it can do, what the recent updates are, and what we'd like it to be in the future. So Radis is a line-by-line code that thrives to be the fastest line-by-line code around. It interfaces today with most databases that you know of. ASA is the latest added to the list, and it can compute 112 molecules and has some non-LT capabilities for CO2. It also has some basic line shape to avoid, and also no lone mixing or no speed dependence so far. It's used to compute spectra when computational speed is a challenge, so mostly for high temperature applications in radiative transfer, fitting models, or to generate CK, SNB models from line-by-line spectra. This is very important in plasma physics and combustion community, where we mostly come from, also in radiative transfer. It can also be used to compare the different databases with the same spectral code. The code was initially started in 2017 as a diagnostic for CO2 splitting by plasma discharges, optical emission spectroscopy in high temperatures, so there are millions of lines. We developed, there was no non-LT code at that time that could do that, so I developed my own and open sourced it. It was the same time that in Eindhoven, Dirk from Bekerom was developing a similar code. We met and decided to build Radis together. Dirk came up with a new algorithm that could cut down on computational speed by orders of magnitude while preserving accuracy. So this became the core of Radis and what we've been developing forever since. And today, people that mostly use Radis is not for the non-LT capacities, but rather for this computational speed. This is what Radis looks like. It's a local Python environment with an object-oriented interface, so you just input your inputs and get spectra. It also comes with two other interfaces I'm going to talk about later. It comes also with the usual post-processing functions, so to crop, offset, interpolate, compare spectra, basic line-of-sight capacities, and one tool I could talk in particular, which is this line survey that allows you to identify the different lines that contribute to your computed spectrum. This is something we use quite a lot. It does retain the non-LT capacities it was developed initially for, so we're talking about multiple Boltzmann distributions, so for vibrational, rotational temperatures, even 300 distributions, so state-to-state vibrational modeling. This is very important in the communities we come from to characterize non-equilibrium plasma or high enthalpy flows like space reentry. It comes Radis with a default set of spectroscopic constants for CO2. Of course, you can use custom ones. And for instance, we've been recently using it to model high temperature non-LT CO2 based on energies recomputed from by rediagonalizing the CSD-SD 4000 Hamiltonian. So that's possible. But the main part is the algorithm. So there are many algorithms implemented in Radis, which is a good lab to compare them. But the main one we use is published in our 2001 paper. And in a nutshell, we qualify it as an on-the-fly tabulation. So in a typical line-by-line code, the bottleneck is the convolution step, which you can see on the left over there. If all lines have the same line shape, instead of convolving each line independently, we just convolve a stick spectrum and run one only kernel, that would be much more efficient. In reality, all lines have a unique line shape, but what we do is take all these parameters that define the line shape, so in a void approximations, got Gaussian width, Lorentzian width, and we create a grid is in this line shape parameter space and simply interpolate and distribute all lines over this grid. So this grid may have 100,000 points. Now we are interpolating millions of billions of lines on the grid. Each point of the grid is a spectrum where where all lines have the same line shape, so we'll run one convolution kernel and then sum up all the grid points. That's very efficient. On the left here, you can see a comparison of the DIT algorithm in red compared to a classical line-by-line approach in black, and we're typically talking about orders of magnitude difference when it comes to millions of lines in the spectrum. Of course, there's an interpolation error, so we've been computing correction coefficients and with error control and prediction. That's in the paper, but in the most general cases, a simple linear interpolation is enough, and actually by refining the grid, you can also have an arbitrary precision. That's very important in some cases. The algorithmic complexity is not linear with the number of lines anymore, and so it's not dependent on the line shape neither, so you can, for instance, use exact line shapes instead of analytical approximations and actually be not only faster but more accurate because you regain what you lost in the interpolation. This, of course, depends on the number of parameters required for your line shape. For non-void line shape, we'll have higher dimensional line parameter space. We'll talk about that in the end. A standalone version of the algorithm is available in the paper, so on GitHub, and I think it is being implemented in the Happy2 code too. Last summer, we came up with a new updated version of the algorithm, which is sparse implementation. So where typically initially the first version could compute lines over, let's say, a vibrational band, the new sparse implementation makes it possible to compute full range spectra. So for instance here, what you see is a high-temp C methane spectrum computed. It's over, we're talking about 25 million lines over 4.5 million grid points computed in over a minute and a half on a single CPU in a laptop. So this is actually quite a very accurate and efficient calculations. The algorithm parallelizes very efficiently. So it's very powerful to add on GPU. Here's a GPU implementation of the algorithm, and what you see is a computation of the asymmetric band of CO2 with CDSD 4000. So this is 250 million lines, 250 million lines here, 300,000 spectral points computed in less than 100 milliseconds. So you actually get live spectra computed, high resolution, of course, which makes it extremely powerful for fitting applications. That was our first mission, was to turn larger databases into spectra. The second is to simplify the interface and to make these databases available to people without any prior knowledge of spectroscopy or Python. We were joined by a very talented software developer, and Elizabeth created this web page. It's available on radis.app from your phone or computer, and you can just compute and download spectra from there. We have HITRAN, ASA, and this week the high-temp was eventually implemented. So what's good is now I have the same interface where anyone can compute spectra from arbitrary database and eventually be able to compare them. We also came up with another solution for more advanced research-oriented use case. This is a Radis lab. It's an online Python environment. You don't have to install anything. Just Google Radis lab and launch it. and it comes with pre-configured and pre-installed HITRAN and ASA. And upload your script there, experimental files, download results, and even share them with colleagues. So eventually it will be live edits like Google Doc, but for spectroscopy. And here we are just building on the strong works that are being done in the data science and tech communities and bringing it to spectroscopy. We think it has some real potential for education and even research cases. Quite recently, it was proof tested by Thibaut Delahaye in the Spec Atmos workshop, where he used Radis lab for the first time to teach basic spectroscopy class to 40 contributors in the class. I'll tell you a few words about how we develop the code. Radis is open source. Code is available on GitHub. We really welcome every new contribution, but beyond this is a growing community of spectroscopy enthusiasts. We have a few developing guidances. One is performance, of course. We try to be extremely fast, but also to share the algorithm. It's a good competition. One is to be robust. So Radis is physically tested on every single change. This is really necessary when you're developing an open source code. This is what allows us to trust the code results. For instance, it happens regularly that the databases we rely on, HITRAN, ExoMol, they update the data with more accurate results, and our test suite sees it and reports it, which shows that it works. We also try to make it intuitive, but also assume always that the user is not a spectroscopy expert, so it's rather raise an error, give advice, than take the risk to return something physically wrong. Here are the core developers who, again, are mostly doing this as a weekend hobby. Good news is some of them are now securing permanent positions in University, and will bring Radis with them, which is secure development in the future. We also became a NumFocus affiliated package this year. So NumFocus is a foundation that's supporting and funding the biggest Python scientific software around, like AstroPy, NumPy. We secure development from grants from there, and we also get regular interns every year from the Google Summer of Code. For instance, presently we have 4 people, 4 interns working on improving line fitting, interface, reducing memory usage, improving the app, or adding non-air diluents. As a perspective for future development, we'll focus on extremely large databases, so typically anything that does not fit in RAM. We currently have a very efficient way to deal with these databases. Redis is actually a good tool to explore them, but we want to be able to implement what we call out-of-core computations, which means that whatever the size of the database and whatever your RAM, you'll always become able to compute it. We want to work on more advanced line shapes, so algorithm requires to create we call a grid in the line chain parameter space. It will scale with low number of dimensions, like speed dependent or key factor additions, but it does not scale up well with large number of parameters. So if I'm taking Hartmann-Tran, I think we're talking about 7 parameters. This is going to be challenging, but we still want to try, and we could use some help here. Final thing for us is to write and release a community paper, including all the people that have been contributing so far. This is the end goal, to be and remain a community developed package. We are quite inspired by packages like AstroPy, for instance, in the astronomy community. And that's pretty much what we want to be, an open standard for open source line by line calculations. Of course, this is the typical joke when you want to be a standard. You start with 14 codes, try to make a standard, but eventually end up with 15 standards. We don't want that, so we are limiting our focus. Radis will basically compute line-by-line spectra from databases and stop there. For the rest, we'll interface with other codes. We also make sure that people can interface with us, and that's our final point. We've started to apply that in real life by integrating with another code called ExoJax, which, if you don't know, I advise you have a look at. It's auto-differentiable, which means it's computed on Jacobian line-by-line code. This makes it very powerful for inference, parameter retrieval, so analysis of exoplanet spectra, for instance. And ExoJax and Radis are working on a common API that will support all databases and actually make our way towards being the open source standard. Thank you.